Hello, so in this video we're going to be carrying on with kind of employing a few techniques, a few little tricks that we can do with second order differential equations. So let's just write down our standard linear second order differential equation, okay, with a monic first term. So in other words, the coefficient in front of the highest derivative, which is the second derivative, is just going to be 1. So in other words, we've divided, say if this was like 3, we've just divided through all the other terms by 3. Okay, so we've just got y double dash, okay, plus some coefficient, it can be variable coefficient times the first derivative, plus another variable coefficient times the function. And let's, for the moment, just consider the homogeneous case. So let's just consider the case where the right-hand side is just equal to 0. Okay, now the thing is, we looked at how we could solve something like this in the last video, and we solved it by coming up with something called the characteristic equation, which essentially we're trying to pull a quadratic out of this. So in other words, it will be r double dash plus some coefficient, same coefficient up here, times r plus the other same coefficient on the end. Okay, and that's still equal to 0. And we basically solved that, and because it's a quadratic, we'll have two roots. We'll have r1 and r2 will have two roots. They could be equal to each other, but nevertheless we will always get two roots out, which means then that we can form two solutions. So y1 and y2. And remember, our general solution that we're looking for, which we guessed, but it does come out that it does work like this, is e to the rt. Okay, so in other words, y1 is e to the r1 times t, okay, so just using that r, and y2 is just e to the r2 times t, so just using that r. Okay, so we've got basically our two solutions out. So therefore, we know that when we have a second order differential equation, we should have two solutions, y1 and y2. Okay, well here what we're going to do, it's a little technique that we can employ, but let's suppose that we know one of the solutions, either it's given to us, or perhaps we can work it out. Perhaps it's a really obvious thing. You know, it's a bit like sometimes you can look at an equation and you can just tell that one of the answers should be that. For example, one of the answers should be 0. That's quite a trivial solution. So in other words, what I'm trying to say is that, you know, sometimes you can just look at an equation and see that one of the answers is just obvious. One of the answers is just obvious. So in other words, we can tell one of the solutions immediately. Or perhaps we might be using numerical methods, which remember, numerical methods are just really glorified trial and error. Okay, so say, for example, if we've got a graph, okay, and we want to work out a certain point on that graph, say, for example, a derivative or a solution or something, corresponds to a solution. Then basically what we do is we do glorified trial and error, and essentially what we're doing is we're moving in towards that point, in some way. And it's just effectively glorified trial and error. And you can use computers and stuff. So perhaps we can find a solution. Let's suppose that we can just find a solution somehow by some method. Okay, the second solution might be a little bit more tricky, but let's suppose we know one solution and we want to find then the other solution. So in other words, we know y1. And let's say, for argument's sake, that y1 is e to the minus 3t. Let's suppose y1 is e to the minus 3t. So in other words, that's the solution that we get. Okay. Well, the idea is that we can now work out what the second solution is. We can now work out what the second solution is from this first solution. Because we know that the second solution should just be some function, let's say v of t, times our first solution, y1. Okay, don't believe me? Well, let's just have a go. So let's suppose that, the second solution that we're after is we don't know the solution, we want to find the solution, but I'm just saying, well, let's suppose that the solution that we're after, the solution that we will end up with is let's say e to the 2t. Well, hopefully you can see that y2 is just some multiple. It's just some multiple. This solution is just some multiple of this one. Because look, if we have y1, which is e to the minus 3t, so e to the minus 3t, and if we multiply it by some function, and that function, sorry, this is e to the 3t, so y2 is e to the 2t, okay? So this is what we're after, and we know that it's just going to be some multiple of this e to the minus 3t. Well, what's it going to be? Are you happy that it's going to be e to the 5t? E to the 5t, because now you can just use the power laws. So in other words, this is my v of t. So this is my function that I have to multiply y1 by in order to get y2. Okay, so let's have a look at this. This is e to the, just by power laws, 5t minus 3t. Yeah. So what's 5t minus 3t? It's e to the 2t. So in other words, my function that I have to multiply by, in this case is e to the, what is it? Yeah, it's e to the 5t. Okay. So in other words, basically the idea is that, our second solution can be found just by multiplying the first solution by some function of t. And the idea is that basically if we can find this function of t, then we can find the second solution, because we know this. We know this y1. Okay, so how are we going to do that? Well, let's, we have our, so basically I'll just write everything which we know out again. So the idea is, okay, so here we have our first, a second order linear differential equation, okay, and we know that one of the solutions from that is going to be this y1 equals something, okay, and we will be given that, or we can find that in some way, okay, and we know that the second solution can be found by multiplying some function by our first solution. Okay, and the idea is that if we find what this v of t is, then we find out what this second solution is. Right, okay, so what is this solution? Well, look, the idea is that, okay, y1 will satisfy this equation over here, will satisfy this equation over here. Okay, well, y2 will also satisfy this equation over here. y2 will also satisfy this equation over here. Okay, and in actual fact, and of course, I've shown you before, that if we write these two things a linear combination of each other, so y equals c1 times y1, so some constant. So yeah, maybe if I just introduce this in the proper way, so y is equal to y1 plus y2. Well, we can also have any constant multiply these, so any number multiplied by these two solutions, and that will also be a solution. Okay, and this is what's known as a general solution. It's just a linear combination of these two solutions. Okay, but basically y1 will satisfy this. Okay, but y2 will also satisfy this as well. Okay, so basically, we know that y2 is going to satisfy this. So in other words, if we plug y2 back in here, then the idea is that we should be able to then find out what v of t is. Let me try and show you, okay, because we know what v1 is. We know what y1 is, okay. So the idea is that basically when we plug y2 into here, so basically what do we need? Well, we need y2, okay, which will be given by this. We also need the first derivative. We also need the first derivative here. So in other words, y2 dash. And we also need the second derivative. We also need the second derivative as well. So in other words, y2 double dash. Right? Well, we can work what y1 out, the first derivative, and we work out what the second derivative is as well, just by differentiating this. So y2 equals v, I'm just going to simplify it to v times y1, but these are both functions of t, okay? So therefore, when we take the derivative, then therefore we're going to have to use the product rule, because these two things are both functions of t and they're being multiplied together, so it's going to be the product rule. Okay, remember what the product rule is. It's the first thing differentiated multiplied by the second thing left alone, okay, plus the other way around, this first thing multiplied by the second thing differentiated. Okay, so that is all the first derivative is going to be. Okay, and then we can find the second derivative, okay, just by differentiating this thing up here. Okay, and this is going to end up with, a little bit more messy, but not too bad. So this is the second derivative. Okay, so it's going to be, let's just consider this first term first. Okay, again, it's the product rule, because v1 dash is going to be still a function of t, and y1 is also a function of t as well. So therefore, it's just two things which are a function of t being multiplied together. So it's going to be v1, the derivative of v1, the derivative of v dash, which is going to be v double dash multiplied by the second thing left alone, right? Plus this first thing left alone, so v dash, multiplied by this second thing differentiated, so y1 dash. Okay. So that's that first thing sorted with. Now let's look at this second thing. Again, it's the product rule again. So that's that first thing differentiated. And so now we're going to do the second thing differentiated. So in other words, this thing differentiated. Well, it's going to be the product rule again, because we've still got two things being a function of t being multiplied together. Okay. So in other words, it's v dash multiplied by this second thing left alone, as well as this second thing left alone, so y1 dash, okay, plus then this first thing left alone, so v, multiplied by this second thing differentiated, so v1 double dash, okay. Now I can do a little bit of simplification. I've got a v dash multiplied by y1 dash here, and a v dash multiplied by y1 dash here. So in other words, I've got v double dash y1. Just combine these two things together, so plus, if I've got the same thing added together, I've just got two of that thing. So v dash, y1 dash, okay, that's that thing sorted with, plus that last thing on the end. So v y1 double dash. Now the thing is, you can either just remember you can either just remember that's y2 double dash, okay? Then the idea is then that we just plug this, we can plug this, plug that, what else? That, give it up, and that back into this thing up here, okay? So let's try and write down again what we've got. So let's just try and plug these three things back into there, okay? So in other words, we've got y double dash, so this thing here, which is v double dash y1 plus 2v dash y1 dash plus v y1 double dash. Okay, so that's all y my second derivative plus a lots of my first derivative. So that thing there. So plus a lots of v dash y1 plus v y1 dash. Okay, plus by. So in other words, plus b lots of that thing up there. So plus b lots of v y1. Okay, and that's all equal to 0. And let's just do a little bit of expanding and simplifying. Okay, so what's this? So we've got let's just expand it out first of all. So we've got v double dash y1 plus 2v dash y1 dash plus vy1 dash double dash plus a v dash y1 plus vy1 dash plus bvy equals 0. Okay, so I've just expanded that thing out now. There should be an a there. So I've expanded that thing out. So now basically just need to collect together like terms. Okay, so in other words, what I want to try and do is I want to try and form some kind of differential equation out of what my v is. Because remember, that's what I want to find. I want to find out what v is. Yeah, in my where are we? In this thing, I want to find out what v is. Because if I find out what v is, then I find out what y2 is. Okay, so that's the idea there. Okay. So let's just try and sort of get this out for v. So in other words, I've got my second derivative there. So I can take my second derivative out. So I've got y1, lots of my second derivative. Cool. Now I'm going to try and do the same for my first derivative. So I've got a first derivative there. I've got a first derivative there. And that's it. So in other words, if I take out a first derivative of this thing, I'll be left with 2y1 dash plus a y1. Lots of v dash, that's my first derivative sorted with. Then I'm just left with my last just function itself. So v there, and there's a v there. So let's add those two together. So we get y1 double dash plus a y1 dash plus by times v equals 0. That's now a differential equation. Yeah, because I've got v, my second derivative of v, first derivative of v, and just v itself. Okay, and then basically, hopefully, I can do a little bit of simplification then. And actually, in actual fact, this thing here, if you notice, this thing here is exactly the same as that thing there. Yeah, I've got y1 dash, so I've just got, my second derivative, plus a lots of my first derivative, so that thing there, plus b lots of just y, so b lots of just my function. Okay, and that should all be equal to 0. So in other words, that whole thing in there should be equal to 0. So in other words, this last thing, because it's just multiplied by 0, should just disappear. And I should be left with this thing, just equal to 0. Okay, and that there I can reduce down to a first order. I can reduce that down to a first order, just making a substitution. Let's say, u equals v dash. Therefore, I'm left with y1 times u dash. Okay, because that means, if u equals v dash, then u dash must equal v double dash. So if I just replace those two things in there, okay, then I can reduce this down to a first order. So plus 2y1 dash plus a y dash times by, what's that, times u, yeah, equals 0. So in other words, that thing there is a first order differential equation. First order, I've looked at all the, I can solve first order hopefully relatively easily. I know all techniques to solve a first order, so I know, in other words, how to solve that. Okay, so in other words, I find out what u is. I know that u equals v dash, and therefore hopefully I can employ just, again, that's just another first order differential equation I've got to solve. V dash equals u. Quite often that's just a case of integrating to find out what v is. I end up with v is. When I find out what v is, then I can find out what y2 is. Yeah, because this is v times y1. Okay, so let's try and do it by an example. I think, you know, sometimes dealing with things generally is a good way to get the ideas in your head, but sometimes for it to really, really click, you want to see it through an example. Okay, so here we have a second order linear differential, or it's not, it is a linear differential equation, but it's using variable coefficients. Okay, so we got t squared, got 3t here. Okay, so it's variable coefficients. Okay, and the idea is that basically, suppose we're given that the first solution, or one of the solutions, is just t to the minus 1. It's just t to the minus 1, okay? So in other words, when we plug t to the minus 1 in there, we should, you know, it should satisfy it, okay? So the idea is then we want to try and find out what y2 is, because we know that y2 is just going to be some function times y1, okay? And we want to basically work out what that function is, that vt is. Okay, so in other words, you know, I'm going to differentiate this again and plug it straight in. Well, I've done all the differentiating before, so are you happy that I'm just going to use the same formulas as I used before? You know, in the exam, I'm never going to remember these in the exam, right? I'm just going to sit there and derive them, but effectively it's just a product rule. So I'm going to end up with v dash times y1 plus, I'll just write them out actually. So here are all our derivatives, you know, of y2 all written out. So basically we're going to need y1 dash and y1 double dash as well. So here's y1, I'm just going to drop the dependence on t because I think it's just going to get in the way. So y1 equals t to the minus 1. Therefore y1 dash should equal the derivative of this thing, so it's going to be minus t to the minus 2. I'm not actually going to write it over t squared or anything just yet. Just for simplicity, as therefore the second derivative is going to be 2t to the minus 3. Yeah, the reason why I'm not going to write over t cubed or whatever, just for the moment, is just because otherwise, well, just because at the moment it's easier to differentiate. But actually we're not going to have to do any more differentiation, so I'm just going to write it now as 1 over t. This is minus 1 over t squared. And this is 2 over t cubed, okay? So now I can plug it straight back into these three things. So in other words, I can get y2, remember, is just v times y1. Well, here's y1. It's going to be v times y1, so v times 1 over t, which is going to become v over t, okay? I'm going to have y2 dash. Y2 dash is going to be v dash times y1, so that's 1 over t. Okay, plus v times y1 dash, so that's this thing, so it's going to be minus times by minus 1 over t squared, so change that to a minus. Okay, and we're going to have y2 double dash, which is going to be equal to v double dash over y1, which is 1 over t, okay, plus 2 lots of v dash over the first derivative, so that's going to become minus, and that's going to become a t squared, okay, plus v times 1 over, v times my second derivative, so that thing, so it's going to become 2 over t cubed, okay. All I've just done there is I've just substituted it in, so this is basically what I end up with. Right, so here are my derivatives. Which I've got here, and here's my original function. So basically the idea is now that I just want to plug all of these derivatives into this function because it should satisfy it, okay, to just try and find out what v is. So let's try and do that. So we've got t squared, lots of my second derivative, so this thing here. So we've got v double dash over t minus 2v dash over t squared plus 2v over t cubed, okay, plus 3t, lots of y, my first derivative, so this is v dash over t minus v over t squared, right? Okay, plus y, so just plus that thing on the end, so plus v over t. That's all equal to 0. Cool, okay. So now I just need to basically try and simplify it and just solve it for v. So I want to end up with a second order differential equation for v. So let's just multiply through by everything, get rid of all the brackets. So this is t squared multiplied by this thing, so it's going to become t, yeah, because one of the t's are going to cancel. It's going to become t squared over t minus 2v t squared, yeah, over t squared, plus 2v t squared over t cubed, plus 3t v dash over t, minus 3tv over t squared, yep, plus v over t equals 0. So t squared is going to cancel with, we're going to cancel here just to end up with t on the top. Okay, these two t squares are going to cancel. Going to cancel with one of them on the bottom, so we're just left with t on the bottom. These two are going to cancel. That's going to cancel with one of those. Okay, and then we're just left there. So, yeah, cool. Okay. Okay, so now I want to try and solve for v, so I'm going to just take out a v double dash here. Sorry, my t's are getting awful. There we go. So that's v double dash here. I'm now going to take out the first derivative. So I've got a first derivative there and a first derivative there. So I'm going to take out I'm going to leave that as a plus. I'm going to have 3, or I could even just simplify it straight away. I could do minus 2 plus 3, which is going to become 1, yeah, plus v dash, yeah, so plus 1 v dash. Okay, and then simplify those three things at the end. So I've got 3 over t plus minus 3 over t. Sorry, what am I doing? Here we go. I'm going to write this as over t. I'm going to write this as over t. And I'm just going to write this as 1 over t. 1 over t times v. Cool. Okay, so I've got 2 over t times v minus 3 over t times v plus 1 over t times v. Are you happy they're all just going to cancel? Yeah, because I've got 2 minus 3 plus 1. That's going to go to 0, so I'm going to end up with 0 over t times v. So that's just going to go to 0. So this is what I'm left with. I'm left with t v double dash plus v dash. That's a first order differential equation, or it is one just kind of hidden. If I let u equal v dash, then therefore that implies that u dash must be equal to the second derivative, and now I can just make a substitution in there. So I'll end up with t times v double dash, which is now u dash, okay, plus v dash, which is now u. And that's the first order differential equation, okay. And I'm actually going to write my u dash as du by dt, because u is a function of t, right? U is a function of t, so therefore when I take the derivative, I'm differentiating with respect to t. Okay, and then if I just take this u over to the other side, I can hopefully use separation of variables. There we go. So I've taken this u over to the other side. Okay, and this is now separation of variables. Okay, so the idea is I want to get everything involving u on one side and everything involving t on the other. So first of all, I'm going to divide through by this u, and then divide through by this t, Okay, then I'm going to multiply through by dt. So I'm going to multiply through by dt and integrate both sides. There we go. And now I just integrate both sides. So this thing integrated is going to become natural logarithm of u. And this right-hand side differentiator is going to become minus natural logarithm of t. Okay, plus some constant of integration, which I'm just going to call c1. Actually, no, I'm going to call it k1. And the reason why is at the end I want to end up with a general solution involving c1 y1 plus c2 y2. Okay, so I don't want to now use c1 in here, okay, because it's a different c1. All right. So there we go. Okay, so I end up with some constant of integration. That is just a constant of integration. I'm just writing it as a k. So therefore, what does u equal? Well, u equals e to this thing, e to the natural logarithm of t plus k1. Okay, similar kind of thing because I'm plus k1 here. This is the same as, this is the same as that. So e times, just by power laws. Okay, and I'm just going to write that thing as, let's going to call it a. Okay, let's call e to the k1. I'm just writing as a. You've seen this 100 times before, which is why I'm going through it quite quickly. Okay, now this is just my logarithm laws. Or even, hopefully you can see that, this is just going to be 1 over e to the ln t. So this is going to become 1 over e to the natural logarithm of t. Well, what's e to the natural logarithm of something? It's just whatever's inside this it's whatever that something is. So in this case, it's just t. Yeah, and I think I've shown you that before. If I haven't, just very, very quickly. Let's suppose I have e to the natural logarithm of x, okay, and I'm going to let y equal that. Okay. So therefore, what's this saying? Well, if I rewrite this to make the power the subject, so in other words, my power is natural logarithm of x, so that's my power, and that's going to be equal to, it's going to be equal to the logarithm of base e of y, of y, yep. Well, logarithm to the base e is just the natural logarithm, right? Natural logarithm of y, so therefore I've got y equals x, because I've just got that thing in the bracket is equal to that thing, these two sides are equal to each other, so therefore, that thing inside the brackets must be equal to that thing inside the brackets, so therefore if y equals x, then this original thing must be equal to x. Yeah, so in other words, x is just equal to whatever is inside, x is just equal to this thing, so e to the natural logarithm of something is just whatever's inside the brackets. Well, here I had e to the natural logarithm of t, so if you like, my t was just my x in this case, or my x in this case, okay? So therefore, I must have t on the bottom, okay? So u equals a over t, so that's what u equals. But remember, I don't want what u equals. I want what v equals. So I now know that u equals v dash, okay? So v dash must equal a over t, okay? Where is just constant. Okay, and so therefore, if I just rewrite this is going to become dv over dt. So therefore, now I can just integrate directly, okay? Because if I say the derivative is equal to a over t, then therefore v must equal the integral. Yeah, if the derivative is equal to that, then v must equal that. If the derivative of v equals a over t, then v must equal the integral of that. It's just the reverse process, right? So what's the integral of a over t? Well, the integral of a over t, if I just take the a out the front and just leave that as 1, that's now natural logarithm. So v equals the natural logarithm, a times the natural logarithm of t. A times the natural logarithm of t. Okay, so now I've got v, my function, which I'm after, was a times the natural logarithm of t. Right. Oops, I forgot my constant of integration. Here's my constant of integration at the end. I'm just going to call it K2. So here's my natural log, I integrate something, therefore I need a constant of integration, that's K2 there. So in other words, V of t isn't strictly speaking that, it's K2. Right, well I know that y2 is equal to V, so my function, this thing, times y1. And I know what y1 was equal to. Y1, if you remember, was equal to 1 over t. Yep, so I now know that y2, so my second solution must be v, which is that thing there, a ln t plus k2, right, times 1 over t, So therefore, if I just multiply this thing out, so I end up with 1 over t multiplied by everything inside the brackets. This is over t and this is over t. Okay, now here I'm going to be a little bit sneaky. Because I've now shown, my second solution is going to be that. But I've got a lot of constants going on there. Which is going to be a little bit difficult to find out without initial conditions. And the idea is that I want to write my general solution is going to be some constant times my first solution, okay, plus another constant times my second solution, So therefore, if I just get rid of these constants, okay, and just leave y2 as that, then that should, in theory, be taken care of by this second constant anyway. So I've got absolutely no problem with getting rid of those constants, because it will be taken care of in my general solution anyway, with this second constant. Otherwise I just end up with constants galore, and they get a bit boring. It actually gets a bit kind of... This is the trouble with differential equations. Sometimes you just end up with so many constants that without any initial data, which we haven't got here, by the way, it can be a little bit difficult, and it can get really, really messy, and it can get quite difficult to work with. So sometimes you have to make a kind of executive decision and say, right, okay, well look, there should be a constant here, and there should be a constant here as well. But because there's also a constant multiplied by this whole thing here, so really there should be a constant multiplied by this thing here, so there'll be more constants multiplied by this thing here. You just say, well look, that thing, let's just say that thing will be taken care of, okay, by this thing in here. So in other words, C2 multiplied by A will just be taken care of by C2. And these two constants, so C2 multiplied by A will be another constant, and C2 multiplied by K2 will just be another constant. So these two things here will be taken care of by this C2 automatically, this C2 in this Y2, okay, in this thing anyway. So basically, I'm just going to make an executive decision. I'm going to get rid of that, okay, and this thing is effectively just a bit of a sort of an extra. Okay, this only comes about because I've been considering constants of integrations coming all the way through. And if you remember, I want y2 just to look nice and neatly like some function involving t times y1. well, look at this first term. That is some function, really neatly, some function, you know, that ln t is my function, multiplied by my y1. If I write it out like this, so ln t multiplied by 1 over t, yeah, that is really neatly looking like that. This sort of baggage term is just sort of getting in the way. So I'm just going to say, make an executive decision, get rid of it. Because it comes about by constant of integration anyway. It comes about because constants, and the constants are taken care of already in there. Okay, so I'm just going to basically say, get rid of it, and I'm just going to say that y2 looks like that. And in actual fact, when you plug it in, it does work. It does work. Okay, so therefore, that's my final solution. So my general solution, so, you know, that's what y2 is equal to, that's what y1 is equal to, okay? So in other words, my general solution will look like c1 multiplied by y1, so that's 1 over t, okay, plus c2 multiplied by y2, well, that's just going to be natural logarithm of t over t. Natural logarithm of t over t. And therefore, that's your final solution. So you kind of have to make an executive decision at the end to basically say, right, all of my constants are going to be taken care of by that c2, and then that sort of gets rid of it and makes it nice and simple.